cartoon diagram shows the 13.7 billion years that it took for our universe to evolve from the moment of the Big Bang right up until today. And we talked already about one of the major constituents of the universe, which is dark matter. And then last week we got started on dark energy. Okay, so this is this component of the universe which is actually accelerating the expansion of the universe. In the very first lecture we chatted about what was the evidence for the fact that the universe was expanding and how this led to the Big Bang model. If things are expanding today and you run the clock backwards, you end up with a Big Bang singularity. And now this notion of dark energy is an unknown component in our universe which is speeding up that acceleration. And it's a very unexpected discovery. So this pie chart of the constituents of the universe, at this stage you guys know all this, right? This is 73% dark energy. You know, the majority of the universe is made up of stuff we really don't know what it is. We're pretty sure of the properties of it. Dark matter, we're pretty sure that's a matter component because of its gravitational effects. That makes it about 23% of the universe. And then the rest of the stuff that is familiar matter is this very, very small component of the universe, the 3.6 and 0.4%. So when we talk about dark energy, we're not talking about a particle, we're not talking about matter. We really are thinking about dark energy as being an energy field. And I started talking about this last week. And maybe this is not a very day-to-day familiar notion of field. What does that mean, right? I don't mean like a field of grass or anything like that, but when particle theorists and people who work in cosmology talk about fields, we mean something that is defined in every point in space and time. So a familiar field that you will all know about is a temperature map. So if we were to look at temperatures over the United States, and all the different colors here represent different values for the temperatures, then this is actually a field. And when it's just a single value, just the temperature in either Fahrenheit or Celsius, we call that a temperature map, and that's a scalar field. A scalar just means a number. And at every point in space and time, you could have this map moving forward in time showing the changing temperature. That is a scalar field. So this is our notion of a field in physics. You could have a more complicated field, so if not only you were interested in just a single number in every point in space, now you wanted to maybe look at wind, the direction of wind, right? So then you have also a notion of not just a value for the wind, how strong the wind is, but also a direction that the wind is blowing in. So those are two pieces of information associated with this type of field, and we call this a vector field. So with dark energy, when we're talking about dark energy being a field, we're thinking about it in terms of this first scalar field component up here, okay, one which just has a number associated with it, which is the energy of the field at every point in space and time, not just in the United States, all over the universe. So also last week I showed you Einstein's equation for general relativity. So we didn't go into the detail of what these symbols mean, but you can really think about the left-hand side of the equation describing the structure of space-time. So the left-hand side of the equation describes the expansion of space itself. And Einstein's equation tells us that this equality sign is telling us that the expansion of space is really driven by all the things in the universe, all the matter and energy and pressure that's in the universe. And this is in this T mu nu component here, the mass and energy of the universe. And then there are just some constants out here in front. So you can just think about this equation in terms of words, that there's a connection between the expansion of the universe and the energy and pressure in the universe. So this is this idea of matter tells space how to curve, and space tells matter how to move. So that's where that expression comes from. So we also spoke last week about all the different evidence for dark energy and how it's a very different substance to dark matter. So one of the things I mentioned last week was this cosmic age problem. We wrote down all the equations that predicted what the age of the universe was, just given matter and energy that we knew about in the universe. And then we compared it with the age of the oldest star clusters that were observed in the universe. And what we found was that the age of the oldest star clusters was older than the age that we predicted from our theory if we don't include dark energy. So we need dark energy in order to account for the age of these massive star clusters. One of the massive observations that really confirmed the existence of dark energy was these supernova observations made by two teams in 1998. And this observation won the Nobel Prize in Physics in 2011. So these massive exploding stars, at the end of their lifetime, they represent standard candles throughout the universe, which allow us to measure distances out to very, very high redshifts or very far back in time. And these supernovae were dimmer than expected. Okay, so they were further away than we would expect in a universe without dark energy. This is even taking into account the expansion of the universe. We really needed to face the fact that not only was the universe expanding, but that expansion was accelerating. And then we also had hints of this presence of new physics, right? Something missing in our picture of the universe coming from the growth of clusters, galaxy clusters in our universe. And then when we did cosmic inventory, when we said, well, what is the total amount of energy in our universe? When we count up all the things we see, and we compared with predictions from what should be there from the cosmic microwave background, we were getting, the cosmic microwave background was telling us that the total energy should equal 1 in some units that make it dimensionless. But when we add up all the stuff we see, all the clusters of galaxies and hot gas in galaxies, and in clusters of galaxies, we were getting a value for the total matter content, which includes dark matter, of only 0.3. So this was giving us this very simple arithmetic of a large proportion, 0.7 or 70% of the universe missing. And that is the component that is in dark energy. So one of the plots that physicists like to show in their papers are these are confidence intervals. So when you hear in the news a 5 sigma detection of the Higgs field, really what they're saying is these different confidence intervals. So these are regions where we think the parameter value lies. And this plot is showing you the amount of dark energy on the y-axis. So this 0.7 is the 70% value. And on the x-axis is the amount of matter in the universe. And you can see at a value of about 0.3, we're landing right inside this inside this yellow contour here. And this yellow contour is combining all the different observations of different probes. So we're combining supernova. If we only had observations of the distances to supernova, we would have these green regions here. So really this is telling you that the value of omega m and omega lambda, the amount of dark energy and dark matter, is not very well constrained. But it's definitely telling us that omega matter is not 1. Okay. We also have observations from the cosmic microwave background, but it's really in combining all these probes. It's listening to all the different physical observations that we have and all the physics that goes into that, where we really constrain the parameter space and we really find that they all agree at a value of 0.7 for the dark energy component of the universe and 0.3 for the matter component. So then this means in our total cosmic inventory, when we're writing down a list of all the things that are in the universe, we have to include this dark energy component here if we want to match observations. So we're familiar with the matter component and maybe the radiation, which represents the photons in the universe. But when we add in this new component, we really need to start asking questions of, well, what are the properties of this? We know the properties of matter. Right? We know the effects due to gravitation. We know that visible matter interacts with light. We know dark matter does not interact with light, but it may have some weak force interaction. But when it comes to dark energy, all we really know is its gravitational effects and the fact that it's a new force in the universe which is accelerating the expansion. So one of the solutions to Einstein's equations tells us what the properties of this new component of the universe are. So this is called the Friedmann equation, and basically the left-hand side of this equation is telling us about the acceleration of the size of the universe. So if you think of the variable a as being the scale factor, the size of the universe, then the rate of change of that scale factor with time is just the acceleration. Okay, so the first derivative of a would represent the velocity, the second derivative of a represents the acceleration. And this is basically how fast the universe is expanding, or accelerating, how fast the expansion is accelerating. The right-hand side of this equation, now we're looking at properties of the stuff in the universe. We're not just saying, what's the amount of stuff in the universe. We're looking at properties like the energy density and the pressure of stuff in the universe. And in order to have acceleration, we need this equation to be greater than 0. Deceleration is W less than 0. Okay. Sorry, that's wrong there. That should be acceleration unless, yeah, we have deceleration unless W is less than 0. So basically, deceleration is a negative sign on the right-hand side here. So what we want is this right-hand side to be positive overall. Okay, we want acceleration because that's what we observe. In order to get that, this parameter W here has to be less than 0. And this parameter W is really key in cosmology. This is what we call the equation of state of dark energy. And it basically is a ratio of the pressure in dark energy to its energy density. And because we need W to be less than 0, and we know that the energy density of something is never 0, or never less than 0, that implies a negative pressure component. So we have these observations of a dark energy representing a force, which is speeding up the expansion of the universe, but it also looks like a negative pressure component. And in order for it to do this accelerated expansion, it has to have these properties. So this is a very unusual property for a substance in our universe to have, and it's not very familiar to us. But last week I spoke a little bit about quantum mechanics and how in quantum field theory, when you have empty space or a vacuum, then in classical mechanics, we think of nothing happening there, right? There's nothing there, nothing is ever going to be there. It's just empty space and energy is 0. But that is not true in quantum field theory. So in quantum field theory, the vacuum is a very turbulent place where we have a non-zero probability for particles to come into existence and then disappear. And during the time that they do exist, they can interact with one another. So we talk about this quantum vacuum as having exactly the same properties of dark energy that we observe. So this notion of the quantum vacuum is never empty, these virtual particles can pop into existence and disappear as long as we borrow energy for a very small amount of time. According to the Heisenberg uncertainty principle, we can do this. And this is why you can really, in a sense, get something from nothing in quantum mechanics. So we think of the quantum vacuum as being a very turbulent place. So this is a computer simulation done by Derek Lineweber in the University of Adelaide. And these are basically taking quantum field theory, so the equations for quantum field theory, which we know agree with observations, agree with measurements in the real world to extreme precision, taking those equations and solving them on a lattice in a computer. And this is basically the quantum vacuum. This is showing the existence of virtual particles popping into existence and disappearing. So this actually represents how turbulent the quantum vacuum is, this energy which is constantly fluctuating. Yeah.
Have we observed these virtual particles?
Yes, we have. Yeah.
In the colliders?
Yes, exactly. So it's at these really high energies where we're able to probe the physics of quantum field theory, and these virtual particles are well studied.
How
So
big,
this notion of the quantum vacuum, yeah.
how big is this area or
This
volume?
simulation? Yeah, I don't know actually. I don't know the dimensions of it. So this is just taking the equations and using a computer to numerically solve the equations of the theory.
But it could represent a very, very tiny...
Very, very small scales, yes. Yeah, very, very small scales. So really quantum mechanics are the laws of physics at very, very small scales. So this notion of these particles popping into existence and disappearing again means that the vacuum is never a boring place to be, but it also means that it has a non-zero energy. And this is exactly the properties of dark energy. So when I talk about dark energy as being a cosmological constant, it means that every particle that exists, there is a non-zero probability for it to appear in a quantum vacuum. And we know that this should be true. This cosmological constant, this energy density associated with the vacuum should be there. And it would represent a negative pressure component in our universe. And this is why one candidate for dark energy is this cosmological constant.
I think somebody up there wanted to.
Okay.
I wonder if you could just say the inventory. How was that done? When was it done? Who did it? Any names associated with it? And is it still going on?
So it's not just that cosmic inventory where we add up all the stuff in the universe.
Right. I mean,
So
how do they do that?
that comes from many, many, many different observations. And in previous lectures, I actually kind of went over all the components in that equation, how we found each of them. But many, many different observations give us that value of omega equal to 1. Is it okay if I ask if we leave questions till afterwards? Is that okay?
Yeah,
I'm
that
going to
would
leave
be-
lots of time afterwards, and we
That
can
would be
do
better.
questions then. Is that good? Yeah. Okay. So the notion of dark energy as a cosmological constant is really appealing because we know that the vacuum has energy density and it has the same properties as dark energy. So this notion of empty space having an energy associated with it, it gives us a very natural candidate for the cosmological, for dark energy, which would be the cosmological constant. So when I say this is a constant, I'm talking about its energy density not changing over time. Okay, so we know that dark energy has not affected the growth of structure, right? And we really need it to be a subdominant component in our universe in order for galaxies to grow, right? We don't need a negative pressure component with a repulsive force of gravity if we're trying to grow galaxies, because we know that gravity is attractive on the scale of galaxies. And then in order for galaxies to grow, they need to fall into gravitational potential wells. And then under the attractive force of gravity, this is how we get stars and planets and things like this. So dark energy, we know it's a smooth component, so this means it does not clump in the universe. So we don't see big clumps of it like we do dark matter. So with gravitational lensing, we covered the evidence for gravitational, for dark matter, and one of the main ones is gravitational lensing, where we actually see this clumping of dark matter. So it really is a familiar component of matter in the fact that it clumps under gravity. So when I talk about this energy density not changing over time, this is actually an extremely important property that dark energy has to have. And I'm going to go through the fact that as the universe expands, the density of different components in the universe change over time. So just to walk you through this in some cartoon example, imagine we have a cube of length L on the side, and we have different mass, different particles inside this box. And each particle has a mass m. So if you like, this box could just represent the universe. Okay, a very, very dull, boring universe where you just have a handful of particles. So the volume of this goes as the cube of the length, one of the sides. And then the density is the mass of each of the particles divided by L cubed. Okay, so the total mass inside this is m. Now if this box was to expand, the number of particles inside does not change. The mass of the particles do not change. So the total mass inside the box does not change. It still stays as m. But now, this box is actually expanded, right? So this represents the expansion of our universe. And say it's expanded by this scale factor a here, which is a function of time. So it may not be a constant, but you could think about it as a constant. At one stage you have a box of a fixed size, and then you just blow that box up. Now, the energy density has actually decreased compared to this earlier time, because the matter has stayed fixed, but the size of the box, the number in the bottom of that fraction, has gotten bigger. So that means overall the density has gotten smaller. So what we say is that as the universe expands, the density of matter decreases as the inverse cubed root of the scale factor. So basically you're just saying that overall the density has decreased because the amount of matter has stayed the same, but the volume of the thing has has increased. What happens now if we, instead of putting particles in there, we put light? We put light particles, which are photons, which have an extra component, which is their wavelength. So we start off at t is equal to 0, a very early universe scenario where we still know the volume of the box is L cubed. We say the energy per photon, we'll just call that E. And then the density is given by the number of photons times the energy divided by the volume of the box. Then we let this box expand. The number of the photons has not changed in this simple picture, but the energy has actually changed. So two things are different when we compare this scenario with the matter. With the matter, the mass of the individual particles did not change. In this scenario, the energy of each of the photons has changed, and also the box is expanded. So if you remember back to lecture 1, we spoke about this already, this fact that as the universe expands, the wavelength of light stretches. And this is this familiar notion of redshift. So as something which maybe started off in the blue band, as the universe expands, it gets redshifted, and now it's in the red part of the spectrum. So this property of the stretching of the wavelength of light is what allows us to make these cosmological distance measurements. So when we compare how radiation dilutes compared to matter, radiation actually dilutes faster than matter as the universe expands. So this dilution now is going to the scale factor to a factor of 4 compared to a to the 3 for matter. So radiation dilutes at a faster rate. So what happens when we talk about this cosmological constant, the dark energy, okay, and this notion of a constant energy? Well, it's just really, really dull. All you're saying is, in the beginning, if you have a density rho in a box of size L, as the box expands, the density stays constant. So this is this notion of cosmological constant. The energy density does not change as the universe expands. But if you take into account what I said about matter and radiation, that their energy density does dilute, it does change as the universe expands, then after a while, you can see that if this number is staying constant, eventually the radiation energy density and the matter energy density will dip below the dark energy density, and this will be the dominant component in our universe. So this picture shows that. Basically, on the x-axis here, we're showing time since the Big Bang, okay, where the axis closest to me is at very early time, so right at the beginning of the universe. The y-axis is the density of each component. And we talk about these different eras of domination, when a component of the universe was the most important thing that was around. So if you were around during the radiation-dominated era, this was a time where the radiation density, which is shown by the blue line, dominated over all the other components. And then because radiation dilutes faster than matter, you can see that there's a point where the two are equal. We call this the matter-radiation equality. And then we enter an era where dark matter dominates. So this is our matter-dominated era. And this whole time period of matter domination is where the galaxies and clusters of galaxies are forming. So this is really important that we have this dark matter-dominated era. And then as the universe expands, we get another crossover point where the matter density and dark energy density are very similar. But ultimately, because the dark energy density is staying constant, we're in an era today where that is the most important component of our universe. So now we're looking at a dark energy dominated era. So the fact that dark energy is subdominant to these two big components of our universe is very important. If it was any different, we would not have galaxies. Okay? If dark energy was the dominant component, you're talking about a universe which is dominated by repulsive gravity. You would never form any galaxies. So one other interesting alternative to the cosmological constant, and one of the things I spent quite a while studying myself during my career, is that, well, what if it's not a constant? Okay? What if it does change a little bit over time? Can you do that? And the answer is, yeah, you can. You can make this dark energy change over time, and we associate it with a scalar field, which now changes in time. It's no longer just a constant. And the kind of nice name for this is quintessence. So this actually comes from, I think it's Greek mythology, where you had your 4 elements that people were familiar with, earth, air, fire, and water, but then the stuff that the gods breathed was different, and that was called quintessence. So quintessence has also been around during the time when people were trying to understand empty space. So what is between planets in our solar system? Is it just empty, or is there actually an ether there? People also associated the term quintessence with that ether. So the interesting thing about it is that this now represents a 5th force in our universe, and the energy density is not a constant over time. So now we say that W varies in time. But if you remember, I spoke about this matter-dominated era where you need matter to dominate the dark energy component. So really, you're only allowed to let this vary by a very small amount if you still want to agree with observations of the growth of structure in our universe. So this is just showing another plot where you have the density on the y-axis, and then this is time. You can think about time on the x-axis. Very early times is now over here where it says quintessence models, and then today is right over here next to me. And instead of having a cosmological constant, which is this red dashed line, which just is kind of dull and boring, it doesn't do anything over the evolution of the universe, now maybe if you have these quintessence scalar fields, their energy density changes over time. But you'll notice they stay subdominant to the black line, which represents the matter component in the universe. And then we also have observations which are telling us that we're living in an expanding universe, that quite recently the expansion has started accelerating. So really, right here, you need all these models to dominate over the matter component. So what goes into these models, that's really something that the theorists need to sit down and work out on pen and paper, and then you need to make sure it agrees with all observations at different epochs in the universe. So it's not a small problem to tackle. But these quintessence models are very interesting. Another thing you can do is you can run n-body simulations. So this is our way of running mock universes using a computer. And this is actually showing us from very early times, they've superimposed here 3 different models. So shown in red, this is basically a dark matter simulation of the growth of structure, which is run in a computer. This is the total dark matter density field here shown in the very back, the light gray area. And they're zooming in to a region which is a dark matter halo. So these are really the birthplaces of galaxies where you would get galaxies forming. And what it's showing you here, the different colors of green, red, and blue, are showing you that you get differences in the formation of structure depending on your dark energy model. So this would actually translate into differences in the birthplaces of galaxies, and that ultimately is constrained by observation. So there are ways of testing these alternative models of dark energy. So, as I said before, we have a natural candidate for what dark energy is, this cosmological constant. So why don't we just accept the fact that it is a cosmological constant? We know that virtual particles exist. We deal with them all the time. So what's the problem? Why don't we just say that's what's accelerating the expansion of our universe? And I mentioned this at the end of last week. We have this very severe problem. It's called a fine-tuning problem, but it really is one of the most severe that we have in physics today. And it's that if we measure the observed value of the energy density that is associated with this dark energy component, we get a very, very tiny number, but definitely non-zero. It's 10 to the minus 30 grams per centimeter cubed. So that's a really, really low density component in our universe. Okay? But it's not zero. So that's a really, really strange thing. Why is it not zero? The second thing is if we say, well, it's the virtual particles which are causing this, then we go away and we understand quantum field theory really, really well. Okay? It's been one of our most successful theories in physics. And then we say, what does quantum field theory predict for this energy density? We get a factor of 10 to the 74 grams per centimeter cubed. So this difference here is huge. It's a factor of 10 to the 120. And this is extremely embarrassing for these theories. And it's really showing us that there's something missing in our understanding. Although quantum field theory is very successful, there really is something missing from that theory. So this is why people look in other directions and say, well, maybe I can explain dark energy in other ways. So if we look at the facts, we know that general relativity and dark matter, if that's all there is in our universe, the theory of general relativity explains our laws of gravity. And dark matter and visible matter, we take into account those and their effects on the expansion. Those two alone cannot explain the observations of the cosmic expansion. And we looked at this idea of, well, what changes do we need to make to our theory? We looked at the idea of adding an extra component to the universe. So this represents adding something in to the right-hand side of Einstein's equation. But you could also look at, well, what if I modify the left-hand side of Einstein's equation? What if I modify our theory of gravity? And then, as always, you need to take into account, well, I can't just, make changes to my theory of gravity. I also have to agree with observations. And this is a really key thing, because general relativity has been extremely successful in explaining gravity in our universe. So is it crazy to think about changing our theory of gravity? I mean, it may sound very crazy. I think the general kind of idea in amongst theorists in cosmology has really changed over the last few decades. So right now, people routinely work on modified gravity theories. But if you're talking about a modified gravity theory which does not include dark matter, I think then you're really talking about fringe cosmology and fringe areas of research to work in. So this idea of modifying gravity, really now people who work in this area accept that dark matter exists, and you're modifying gravity in order to explain dark energy, right? Because the evidence for dark matter is very, very heavy, and we've accepted it. So we can look to history and we can say, well, stuff like this happened before, this constant argument amongst theorists of whether or not to modify gravity or to introduce a new component in our universe. So one of the first interesting cases of this is that when we had Newton's laws of gravity and people were observing the motions of planets in our solar system, at the time, the furthest planet that they knew about was Uranus. And they were using Newton's equations of motion to predict the orbit of Uranus. And they noticed irregularities in this orbit which really deviated from the laws according to Newton. And we had one astronomer called George Airy who believed that these irregularities in the orbit could be explained by a deviation in Newton's laws to gravity. So this is an example of someone who wanted to modify gravity in order to explain observations. And then we had two other astronomers. Adams at the time was actually just a graduate student. And he thought that these observations could actually be accounted for if there was a new planet which our telescopes were not strong enough to see. And this is actually how Neptune was discovered. Okay, so we actually then found out later on that these irregularities in the orbit of Uranus were due to the presence of an extra particle in our universe, if you like, an extra bit of matter, which was Neptune. Another story which went the other way was the precession of the perihelion of Mercury. So as Mercury goes around the sun, there's a point at which it's closest to the sun. We call this the perihelion. And if you take Newton's description of gravity, then there were these very significant deviations in the predictions for the orbit of Mercury and what Mercury was actually doing. And at this time, you had astronomer Leverrier, who was the same guy as on the previous slide. Leverrier here had correctly predicted the existence of a new planet. In this case, Leverrier thought, well, now we need to modify our theory of gravity to explain this. Mercury's doing something strange, and maybe we need to modify our theory of gravity in this case. But it turns out, Leverrier thought there was an extra planet. I'm getting it wrong now. Leverrier thought there was an extra planet. He nicknamed this Vulcan. He thought Vulcan would explain the existence of these deviations from Newtonian gravity, but it was actually Einstein's theory which turned out to be correct. Einstein wrote down in his curved space-time what you would get for this precession of Mercury, and it turns out that he was correct. In this instance, we did need to modify our theory of gravity. So this constant interplay, or this arguments between theorists of whether or not to introduce a new component or modify gravity is not new, and history has taught us that either side can be correct. And really modifying gravity, it may feel like a very extreme thing to do, but if that's the way our universe is, then we just have to accept it. So when we talk about dark energy accelerating the expansion of our universe, we know that this is a really big scale problem, right? We're not talking about day-to-day things which we see on Earth. We're talking about the motion of astronomical objects. We're talking about galaxies and clusters of galaxies experiencing this force. So really, the dominant force when you talk about these scales is gravity. So of the forces that we know about in our universe, the electromagnetic force, the one that's associated with light, is the most familiar. This is not a dominant force on these scales. When you talk about what happens with the electron and proton in an atom, and even within protons themselves, the dominant force there is the strong force. That force has no say on galactic scales. It's very, very weak. We also have the weak force, which, as you can guess, is very, very weak. It does not have a say on these scales. So really, of the forces we know about, gravity is the one that we should be looking at if we want to explain the accelerated expansion. So how do we think about changing gravity? I mean, how do you do that? How do you write down a new theory? Well, you have to take into account that there are theories that have come before which are incredibly successful in different regimes. So we have Newton's description of gravity, which we know is very accurate if we just want to calculate things like masses close to the surface of the Earth. So projectiles, for example. If you have a cannon being fired, then Newton's gravity, his description of gravity, which is an inverse r squared law, so basically the force between two particles goes as the inverse of the distance squared, then this is a very accurate theory. And this is a nice art installation which was shown in one of the buildings in the University of Cambridge in the UK to celebrate the discovery. It was an anniversary of the discovery of Newton's equations, with this fabled story of an apple falling on its head where he realized the law of gravity. So close to the Earth, we know we can't really modify Newton's gravity. Okay? We know that that works, and we don't need to reinvent the wheel. When we move a little bit further out and we say, okay, well, now what about around the Earth? If we look at satellites and how they move around the Earth, well, what theory describes that motion? And if you're only interested in a very crude approximation, then you could use Newtonian gravity to describe the orbit of satellites around the Earth. But in order to be very precise, and at the level of GPS, for example, we need to take into account general relativity. So the very interesting thing about GPS is that GPS needs to take into account special relativity. So this is particles that are traveling close to the speed of light. It needs to take into account the effects of special relativity, but also general relativity. So the reason it needs to take into account general relativity is that the Earth is a massive body which is actually curving space-time around it. So this is what Einstein's general relativity told us. Okay? Matter is telling space how to curve. And this satellite is actually traveling around the Earth, and it's traveling in this curved space-time. So the clock, which is on the GPS satellite, is being affected by the motion in a curved space-time. Whereas clocks here on Earth, we're not being affected by the curvature of space-time to the same extent. So in order for GPS to be accurate, which it is to about 15 meters for some commercial GPS products, we really need to take into account this delay in transmitting messages to the clocks on the GPS satellites and then relaying it back to Earth. And if we were not to take into account the effects of general relativity, GPS would be way off. Okay? All airplanes would basically they would not get to their destination. So that's one interesting thing about when you have to take into account accuracy, even at the scale of satellites, we really need to move from Newtonian gravity to general relativity. So what if we move further out then on solar system scales? So as I mentioned before, when we looked at planets like Mercury and how that orbits around the Sun, in order to make really accurate measurements, we needed also general relativity. So general relativity, and I'll talk about this more in a few slides, has been really, really well tested in our solar system. So we cannot modify our theory here, and we need to stick with general relativity. When we go further out and we look at other galaxies and how they clump together, general relativity also explains those observations. The bending of light around clusters of galaxies is perfectly explained by general relativity, and we don't have any deviations from GR in these environments. So now we need to even look on even larger scales, right? And now we're talking about these scales where the universe itself is undergoing an accelerated expansion. Another interesting thing is that GR has been very well tested in these dense environments where there are lots of galaxies clumped together and they're causing massive gravitational lensing effects. GR has not been so well tested in empty spaces. So for example, voids where there may be one or two galaxies. And so in these places, we may look for deviations from GR. And we can write down different theories where we have a deviation or a difference from GR, but then we have to also take into account all these other scales where our theory needs to look like GR, and then it needs to look like Newtonian gravity. So this is like the challenge that faces a theorist who wants to write down a modified gravity theory. And then there's the annoying success of both of these theories. Okay? So if you're looking to make your name in modified gravity, it's very annoying that both of these theories have been so successful. So I'm going to go through some of the really beautiful measurements that have been made to show us that general relativity is the correct description of gravity. So one of the first and earliest ones which really confirmed GR was this perihelion shift of Mercury, which I spoke about already. And now we have measurements of this which are at the level of 0.3%, so confirming GR as the correct theory of gravity at that level. This is another astronomical body in our solar system, and we're able to make measurements to this level of accuracy. There's also another interesting prediction of GR, which is that light which travels past a massive body, this massive body being the sun, which actually deforms space-time around it, the light which travels from a satellite gets deflected by the massive body. It's traveling in the curved space-time and on its way to us. So this deflection slows down the flight time of that light. And that has actually been measured. So the Cassini spacecraft, which made its way to Saturn, that was its primary mission, was to study Saturn. But on its way, as it passed around the Earth, we sent messages back from the Cassini spacecraft to the Earth and actually measured this, what it's called Shapiro time delay. So this Shapiro time delay has to be taken into account when we're sending satellites this far out in the solar system. It's a non-negligible correction, and it perfectly validates to exquisite precision the predictions of general relativity. Another really interesting experiments which are still ongoing are these lunar ranging experiments. So the Apollo missions, which started in the mid-1960s, they carried up with them deflection, so these are solar deflections, basically laser beam deflection panels. And they left them up there on the moon, and they're still up there today. Okay? And then we have several observatories around the world. This picture here is from the NASA Goddard Space Flight Center, where they're projecting a laser beam at the moon, and it's reflecting off these panels that the astronauts left off there, and then the beam is coming back down to Earth. So these lunar laser ranging experiments have measured our distance to the moon to a millimeter precision. Okay, so this is the width of a coin precision experiment. So this is really amazingly beautiful experiments. And how does this test GR? Well, GR has a very particular prediction for how fast bodies are moving around the sun and the motion of those bodies. And this perfectly agrees with this. So this is this notion of a universality of free fall, how fast bodies are falling in a gravitational field. GR tells us about that. And these measurements of the distance to the moon have perfectly confirmed the predictions of GR. The really interesting thing about these experiments is that because you're shooting a massive laser at the moon, you have to be careful of aircraft flying over. So apparently they have spotters on the ground here, and they check for any rogue aircraft. So they know the flight path of normal commercial airlines, but any rogue aircraft that are out here, they have a massive panic button apparently they can hit and turn off the laser. It's a fun job. Another really beautiful experiment which finished now, I think it was in 2008. This was Gravity Probe B. And I really like the quote from one of the guys on the team here. He said, "All we need is a perfect gyroscope and a perfect telescope and a perfect vacuum in a perfect chamber in an orbit 400 miles." And they did it, right? This experiment finished in 2008, and they confirmed this frame dragging effect. So, as I mentioned before, you have the Earth sitting on space-time, if you like. It's deforming the space-time around it. And the fact that the Earth is orbiting and actually, it's actually dragging space-time around it. So this is this notion of dragging of space-time around a massive body that GR predicts. And in this experiment, what they did was they put 4 gyroscopes. So this is an animation here of a gyroscope precessing. 4 gyroscopes in orbit around the Earth, and measured the deviation in the precession of these gyroscopes and compared it with the predictions from GR due to this frame dragging effect. And as you can imagine, these are very, very small deviations, right? Because the Earth is not a very massive body compared to other astronomical objects. And so the level of the experiment was on milli-arcsecond scales. So just to give you an idea, what is a milli-arcsecond? You can think about this triangle here, which is going between Paris and New York. And what we have here, which is closing the triangle, is something the size of a quarter. So these measurements are measuring something which is the size of a quarter, but this angle here is a milli-arcsecond. So something which is very, very tiny angle. And these measurements all beautifully confirmed the predictions of GR. So this is what I mean when I talk about the annoying success of this theory. It's really remarkable. We have more evidence, okay? So even further out, in more, we talk about stronger gravity regimes. We have measurements from these binary pulsars, which are rotating neutron stars. So basically, very, very dense stars just made up of neutrons. They're orbiting one another, and they're actually interacting and losing energy due to very high energy photons. So they act as massive telescopes, massive beams of light in our universe as they rotate around. They're also very heavy objects, so they cause massive deformations to the space-time around them. Okay. And as they're spiraling around one another and interacting, what actually happens is they're deforming the space-time around them, and they're causing these ripples of space-time, which we call gravitational waves. And because the gravitational waves represent an energy which is lost from these particles, then we can measure the loss from the particles. We can measure the loss in energy because of the light coming from these binary pulsars. And this is not a direct detection of gravitational waves because we haven't directly measured or found gravitational waves. This is an indirect detection of gravitational waves, which is perfectly aligned with the predictions of Einstein's general relativity. So binary pulsars basically give us an accuracy of 0.2% in confirming GR. Then what about in the lab? So people are doing really remarkable experiments here on Earth to look for deviations of very small scales to the theory of gravity. So before in previous slides I was saying, well, gravity is a large scale force, that's where it's dominant. That's true, that is where it's dominant, but gravity, the effects of gravity should be everywhere, right? Just in the lab it's a very, very small effect, and that makes the experiments even more difficult to make. So there's a group at the University of Washington which are doing these torsion balance experiments. So basically you have two rings which are rotating around past one another, and they're measuring the torsion, the effect, the turning effect of gravity due to these two plates in close proximity to one another, and you can measure the deviation of gravity and compare it. But you can measure any deviations from gravity would really be a huge signal that GR is breaking down on small scales here. These experiments are extremely difficult. So apparently they make their best measurements very late at night because there's nobody driving in the car park next to the experiment, because this experiment actually picks up vibrations from cars driving inside the building. Okay, so just to give you an idea of some of the equations that you need to look at every day if you want to modify gravity. So if anyone's interested, I encourage you to go off and do these equations yourself. It's a lot of fun. So it's really tough to modify gravity, okay? Because as I mentioned before, all those experiments are showing us that GR is right on all those scales that we know about, and we have to look into maybe voids, very underdense regions, or very, very large scales, and then maybe we could modify gravity in those places. But it's a really non-trivial thing to do. But why would we even bother doing this? Okay, we know GR has been well tested in all these different environments. But the other interesting thing about GR is that it actually predicts its own downfall. There are areas, and we know about these regions called singularities, where the laws of GR do not apply. And they really do not tell us anything about singularities, for example, black holes. So black holes represent regions of infinite density in a very, very small volume. And the laws of GR really cannot tell us anything about the interior of black holes. So I just want to show you this nice movie. This is actual data of the motion of stars in our own galaxy, the Milky Way, around our central black hole. So you can see here at the center, this is basically where the central black hole will be. And the motion of these stars at different distances allows us to measure the mass of the black hole. So that's really all I wanted to say about modifying gravity and dark energy today. And then next week we'll go on and talk about computer simulations and how we actually do those and simulate the universe in a computer. Thank you. So any questions now? Please stay and ask questions if you have some. Yeah.
You mentioned repulsive gravity. What did you have in mind?
So the effects of dark energy act like a repulsive gravity. Exactly, yeah. Yeah. Yes?
You answered this to some degree, I guess, but what can you say about the uniformity or lack of dark energy?
So the fact that the energy density is so low.
Is it in any way uniform?
Yes, so that's one of the key things, is that it's a very smoothly distributed component of our universe. And the fact that it doesn't clump is very important. Or if it clumps at a very small level.
Can it be mapped yet in any way?
No. All we know, if you are going to form the galaxies that we see, then it needs to be smoothly distributed. It cannot clump. And in terms of measurements, all the measurements I talked about, which are testing GR, if there was any clumping of a dark energy component, which had a repulsive energy, this would have a huge impact on precision experiments like gravitational lensing and measurements of masses and things like this. So we would see those effects if gravity clumped to a large extent, but we don't see those. Any other questions? Yeah?
Pre-Copernicus astronomy was constantly made to work by adding epicycle so that you could account for retrograde motion and so on. And I wanted to ask this with that in mind. Since quantum theory on the one hand and also the Big Bang inflationary theory were developed without any knowledge of dark matter or dark energy, shouldn't they be revised from the beginning to see that they were all the way through instead of patched up at the end?
Yeah, that's a good idea. I mean, I'd encourage you to do it if you wanted to. It doesn't sound like an easy thing to do, to be honest. Yeah. Any changes you make are incredibly hard to follow through and be consistent, and that's one of the key things now. Our measurements, our observations are so precise, right? With the theories we have, any change you want to make is very difficult.
Okay, thank you.
Yeah, when you describe the path of the light going through around the sun,
Yes.
and said that it changed the time that the light traveled, is because the path was longer. not
Exactly.
because- Yeah.
Yeah, very good. Yeah, very good. Yeah, thanks.
When you were talking about the cosmological constant as a candidate, you had a graph or a picture that showed with the expansion of the universe, the energy density staying the same.
Mm-hmm. Yeah.
So you have a larger universe, energy density is the same. And to my simple way of thinking, that speaks of more energy after than before, which when I asked you about last week, you said is not the case. There is no more energy.
Yeah.
So does your answer imply that you're not accepting the cosmological constant and you're going into altering?
No, so you can have a cosmological constant and no new energy being introduced. So in this plot, the total amount under all these curves adds up to the same thing. So what I'm saying is, imagine in the very beginning, you had zero dark energy. This is just some cartoon example. And we said that we had 100% of everything in the universe was dark matter. And then we know that dark matter dilutes as the universe expands, and let's say the energy density starts to rise in dark energy. The total amount is still 100%, right? It's just the distribution between dark matter and dark energy. The total amount of energy in the universe is still 100%. As the universe expands, the amount of energy which is in dark matter decreases, and then dark energy stays a constant in this picture, but the total amount is still constant. It's just the relative amounts that are in radiation, dark matter, and dark energy.
I'm not sure I'm understanding. Does that mean then that the source of the dark energy, it's getting something from something else?
No, so it's really this. So it's this cartoon picture that I showed you before of this box expanding. Okay, there's a loss in the density component here. Right, you have this equation which tells you that not only is the universe expanding, right? So L on the bottom of the fraction here is increasing. The energy is decreasing on the top. So you can have this interplay in the fraction where you haven't added any new energy, okay, but the total amount has gone down over time, which is in radiation. So you really need to think about it's the dilution of the energy which is in. It's not that the different components, some amount of energy in dark matter goes into dark energy. It's not that. It's the relative importance of these components as the universe expands over time.
I'll put it in my pipe and smoke it.
Yeah.
If you double the volume of the universe,
Yeah.
and you keep the density of dark energy constant, aren't you increasing the total amount of dark energy?
No, so the density goes as the amount of stuff. So it's the energy density which is constant, not the energy. And energy density is energy over volume.
But if the density is constant and the volume increases,
The energy density is constant, yeah.
it seems like you have more energy.
So the energy, you can think about it like that. The energy is increasing, but the total amount of energy in the universe is not increasing. Right? It's the energy density in that component which is staying a constant. So it's the relative.
Well,
interplay
where's
of
the-
those three.
If I have, a certain amount of cotton in a box,
Yeah,
and it's a certain, density,
yeah,
and I add another box of the same size with the same density, I've got
yeah.
twice as much cotton.
Yeah, so you can think, so these plots, I'm showing energy density, which is not increasing. Okay, when you talk about just the energy, then yes, the energy in the dark energy is increasing. But
Okay, where's it coming from?
So the energy here, so it's the energy in a certain volume. So I think in terms of, if you want to think about it in terms of the energy increasing, if it's the cosmological constant, then it's these virtual particle pairs are starting to dominate very late on.
Even though they were only 120th orders of magnitude small?
Yes, yeah. So definitely you do have interplay between different components of the universe and energy. I mean, we know this, right? Energy is passed between different components of the universe, between the radiation component and the matter component. But in terms of dark energy, we don't know. We don't know. All we know is that the gravitational effects of dark energy. We don't know that it interacts in terms of light. Like, is light giving... I mean, it's a dark component, so we know it does not interact with light. So in terms of where is this energy coming from, this is one of the properties that we don't understand, right?
Okay, another problem with the fluctuations of virtual particles.
Yeah.
Why don't their effects cancel out?
Just hold on 1 second. Yeah.
Why don't the effects of the these virtual particles that come into existence and disappear,
Yeah.
why don't they contribute zero because they cancel each other out?
No, so the time scales you're talking about, when I showed this movie of the fluctuations, on the small scales, these fluctuations pop into existence and out of existence, but overall on a longer time scale you end up with a non-zero energy in the vacuum.
But when it pops into existence, you said it was borrowing the energy from somewhere else, which is, if this is pressing outwards, where it's borrowing from, it's pressing inwards.
But that non-zero probability for the particles to always pop into existence in a vacuum never goes to zero, and that corresponds to a non-zero energy of the vacuum, which is always there.
But why doesn't it cancel out?
There's no cancelling out because it's not like you just have a single particle. So a single particle pair can, I mean, where's the cancelling of energy?
You said the energy is being borrowed. So if you have a plus energy from here, you get a negative energy somewhere else.
So in a sense, I'm talking about borrowed in terms of, you think about the vacuum as having zero energy, right? And then suddenly we create a positive energy. It's the notion of you can do this for a small amount of time as long as they disappear again and give a fixed constant for the vacuum. So a non-zero probability for particles to exist, then some particles may pop up. You don't just get one pair, maybe you get three. That could be considered as a violation of the energy that's in that vacuum. But you can do that for a small amount of time as long as you repay them and then set everything back to the constant energy that quantum mechanics predicts. Because you don't just get one particle being produced, you could get lots, right? It's this notion of it fluctuating. And it's allowed to fluctuate. So there's a mean value for the energy, but you have fluctuations around that mean. And how are you allowed to do that? Because are you robbing energy from somewhere and repaying it in other places? You're allowed to fluctuate from the mean energy of the vacuum. Because if you pay it back in a certain amount of time, then you're okay in quantum mechanics.
But if you have that mean energy, there's no need for fluctuations because you have energy there already.
But it's not that we introduce those fluctuations. Quantum mechanics tells us those fluctuations are there. It's not an artificial construction. Those fluctuations exist, and we're just trying to understand how can you do that.
But it seems like you wouldn't need them at all if you already have this basic medium of energy.
But I mean, need them. I mean, this is the
No,
way the
no.
universe is.
I mean, why bring them in if it seems like they're an extraneous factor that don't really contribute anything, because you already have that
This is our
energy.
description of the quantum vacuum. This is how it is.
Yeah.
I mean, you can say we don't need it, but I mean, that's the way it is.
I don't see how it contributes anything. But sorry.
But what I'm saying is that the non-zero probability for the vacuum to have energy, that gives us a non-zero mean energy for the vacuum, and that is the dark energy. And then you have fluctuations of the virtual particles around that non-zero probability for virtual pairs to exist. And then the fluctuations around that mean, how are we able to do that? That comes about due to Heisenberg's observable principle. But the mean non-zero energy of the vacuum, that is our candidate for dark energy. Okay, and that is tied up into the whole theory of how we even get virtual particles popping up. Do you see what I'm saying?
Yeah,
So it's a detail around the fact that it's the quantum vacuum, which is a non-zero mean energy.
Yeah, I can understand the mean non-zero, but the fact that you also talk about fluctuation seems to be extraneous.
Well, because people, when you think classically, people are like, well, there's no energy in a vacuum, right?
Yeah.
And then there's the idea of, well, we know that in quantum mechanics, it's just basically building up this picture of the vacuum having a non-zero mean, but then you also have these fluctuations around the mean which represent these virtual particles. So basically, I'm just trying to fill in a more complete picture of the quantum mechanical vacuum, which is a bizarre place.
It only fluctuates in one direction, though, to create energy. It doesn't fluctuate in a negative direction.
Yeah, exactly, yeah. Any other questions? Yeah, in the back.
I missed a lot of that, I couldn't hear it. But the virtual particles, have they been proven, observed, or is it just all theory?
No, they've been observed, yeah. So in the lecture last week, I talked about Casimir experiments. So these are deviations in the electromagnetic field due to geometry of the experiment. And in that, we do measure these virtual particles, which are associated with the electromagnetic field. So yes, virtual particles, you see them as well in these collider experiments. So particles which are being collided together at very high energies, you see these virtual particles as kind of energy loss, which then may reappear as other particles. So this notion of energy being transmitted into matter and then maybe back into energy and back into more matter, this is really something that we probe in the colliders. So it's not just theoretical. Maybe take one more question? Yeah.
It's about that graphic that you have, that the volume is expanding and the photons that you have in the drawing. Well, the photons didn't show that they were stretched, they show bigger. That is a confusing thing.
Oh, the graphic of the balloon? Yeah, the graphic of the balloon is never, it's never a good analogy, I guess.
Yeah, but the other thing is that as the space expands and these photons stretch by losing energy, being of less frequency, where is any accounting for that energy that it was lost?
So basically you're talking about the kinetic energy of the photon as it's traveling over a greater distance. So it's taking longer for the photon to get to us.
And so nothing changed.
So yeah, there is energy loss. This is the
where
redshift.
does it go?
So basically this is kinetic energy that is just lost to the system. So it's basically, because the universe is longer, it's taking more energy for the photon to travel to us. So the energy itself is being lost to the system. And yes, we see this as the redshifting effect. Yeah, if you don't mind, you can ask me afterwards and we'll just wrap up there. Thank you very much.